I'm just going to start off doing maybe some bullet points from basically the highlights from this week, right? So it is, what week is it? It was March 24th through March 28th. So let's see. The first thing we talked about was carbonyls. Right? They're all C double bond O's. Right? We talked about ketones and aldehydes are types of carbonyls, but we kind of put those guys in a box. We're going to wait to deal with those guys in later chapters. For this chapter 16, right, we're in chapter 16, we're going to talk exclusively about carboxylic acid groups. So carbonyls that have a good leaving group on them, or have a leaving group on them at least. All right, so we talked about acid chlorides, talked about esters, talked about carboxylic acids, we talked about amides, and we also added in there anhydrides. So the other big thing is we showed these 5 different types of carboxylic acid derivatives. We also talked about, are they all going to react in the same rates, right? Is one of them more reactive than the others? So we said, I think, that acid chlorides are more reactive, basically meaning the carbon of the carbonyl group here is more delta plus because electrons being withdrawn, and also because when we make that tetrahedral intermediate, right, we're going to form a good leaving group. Number 2 was anhydrides, right, because this leaving group is stable. Why is this leaving group stable? Has resonance capabilities, that's right. Now the acid and the ester were tied for 3 and 4, right? Because O minus is O minus with OH or O with carbon, so that's a localized charge, still not very good. And then lastly were the amides, and that's because, right, a nitrogen with a negative charge is not very stable, right? It's pretty reactive, so that's not likely to happen. Good. So we took this a step further and we talked about some physical properties that kind of fell out from these ideas. And the biggest one we talked about was boiling point. So the ideas we got from the physical properties about the boiling point was that if you have resonance, if you have polarity, just polar bonds, and if you can H bond, do hydrogen bonding with yourself, all of these things will increase the boiling point of your molecule. Let me show some specific examples and things like that as well. All right, so the next thing we talked about was essentially these sp2 hybridized carbons of these carbonyls, and kind of breaking down the molecular orbital picture here, and realizing when we do reactions with these, they're not SN2 reactions. So these reactions we're going to do are not SN2. There's something called addition, then elimination. Right, something adds and then something eliminates. So let's first draw the molecular orbital picture, see what a carbonyl looks like. So we have a C. Right? So I've drawn here the pi bond, right? You can notice that the lobe is bigger on the oxygen because the oxygen is more likely to have the electrons in a pi bond, right? Because it's more electronegative. So in all these reactions, if you want to break a pi bond, where do you need to put electrons? In pi star. So we got to figure out where pi star is at. So pi star is where electrons are less likely to be at. So in a polar bond, the less electronegative atom has the bigger antibonding orbital, like pi star. So in this case, carbon is going to have this big pi star, whereas oxygen will have a little one. Right? And when nucleophiles come in, they attack pi star and break the pi bond. And they can attack from either the top or the bottom. Either one's open. All right? Okay, so with this idea, this molecular orbital picture in mind, let's just show a reaction. Right? So what happens if I take an acid chloride and react it with NaOH minus N plus, right? So we talked about the carbonyl of the carbon being the electrophile, so that's what we're going to attack. So what we'll attack is that carbon. We know it's not an SN2 reaction because the pi bond, right, the sigma star would be hard to get to because the pi electrons would be in the way, so it's not SN2, so it's in an addition, which is the first step. We're adding something in. Equilibrium arrow is important. All right, we balance our charge. So Na plus is kind of along for the ride. So now you have a tetrahedral intermediate, right? So we have this tetrahedral intermediate here, and we have to make a choice, right? Do we want to stay here, or do we have another good leaving group? And what leaving group is the best? That's what we want to kick out. So the best leaving group here is the Cl. So we'll bring these electrons down. Cl goes there. All right.
Do the Na and Cl come together then?
That's right. So now we have this and the OH. We just kicked off Cl minus and Na plus. Right, so we made NaCl. Notice the big points, remember, are equilibrium arrows, right? All these equilibrium arrows. And the reason why this reaction goes is because we're starting with something that's more reactive, right? We're starting with something that's an acid chloride. That's more reactive than an carboxylic acid, right? The other way to look at it is OH minus versus Cl minus. Which one's more stable? Well, Cl minus is bigger. It's more electronegative. It's happier with a negative charge, so it's more likely to go that way.
See, with that, when you start getting more complicated molecules, it gets trickier to see which one's the better leaving group.
Yes. So the trick is remembering back to your reactivity table, right? Who's more reactive? What's the order of reactivity for these things? That's the trick to remember that, right? That acid chloride is more reactive than an ester. Right, that's the key, is in knowing those 5 things, right? Backwards and forwards. Who wants to react where and which way.
So
So it really depends on which way you're going, right? And don't forget those free energy diagrams we did as well. Those are really important. It'd be nice to look at. Look at a homework problem where they're using a cyclic amide, which is called what? A lactam, right? Right. We're going to react this with H plus
what number is this?
in water. It's number 15 or 16? 15. Right, so again here, we've done this. So the thing is, what I'm trying to get you guys to do is to translate, just because it's an amide, it's not any different than an ester, which you've already done, right? So the idea is still stay the same, right? Where if you have H plus, you got to use that first. Right? Use that H plus right away. So what does H plus do for you? Right? What's the point of the H plus here? It protonates the carbonyl, which makes it a better electrophile, right? Because are amides very electrophilic or naturally? No. So you need to make it better, right? So you'd use H plus. And so once you use that H plus, now water can get involved. Right, and be a really good nucleophile. Or be at least a better nucleophile, because this electrophile is better. So now you get to this tetrahedral intermediate. Notice, what kind of conditions are we under here? Acidic, so we always have to have a what overall charge? Positive. So one of the things I've been seeing a lot of is people do not balance their charges. Always got to ask yourself, did I balance my charges, right? Right. This water here, right, gave up some electrons. It's going to have a plus charge, right? It gave up some electrons. Somebody else got electrons back, so it's no longer going to have a plus charge. So now at this point where you have this tetrahedral intermediate, right? You have a tetrahedral intermediate. What they're going to say, when you heat this up, you're going to be able to break this amide bond, right? At the end of the day, we're trying to break this amide bond. So that means we're trying to break this bond right here. It means you have to open the ring, right? But right now, as it stands, my best leaving group in this tetrahedral intermediate is this H2O, but that's what I just added. I don't want to make that a good leaving group. I want to break this bond, this carbon-nitrogen bond. So if I want to break that carbon-nitrogen bond, I need to put the H on the nitrogen. So I can say proton transfer. So now the nitrogen, what's the best leaving group now in this tetrahedral intermediate? It's this guy. The nitrogen is now protonated, right? Proton transfer. So if that's the case, right, now I just want to bring electrons down. Either one is fine. Now I've broken that carbon-nitrogen bond. And I know a bunch of everybody loves the number of carbons, but this is going to start to become important, I think. You know, what do I know? I just do this for a living. Right? Because if you lose a carbon, you lose points. So in this case, this oxygen is donating electrons, this nitrogen is getting electrons, so it no longer has a plus charge. So the plus charge now is on this oxygen here. And I would also add that this is catalytic, right? So what's going to happen is that these electrons are going to go back. And then you've lost minus H plus. All right. But this is a little bit of a, not tricky, but makes you think a little bit more. And you also have H plus still floating around. So here's the deal. You have a carboxylic acid and you have an amine. Will either of those react with H plus? Or which one's most likely to react with H plus? The nitrogen is, right? The nitrogen is more willing to donate its lone pairs. So what happens is this nitrogen reacts with that proton, that H plus. So the final real product is where they'll ding you on the homework, perhaps. There's a plus charge overall on the nitrogen at the end.
So why would nitrogen want to be charged? I mean,
Versus H plus.
I know it's
So it's either, there's gonna be a plus charge either way. So either have nitrogen with the plus charge or the H plus. Nitrogen is basic enough it'll react with H plus. Okay, H plus is really unstable, right? So you'll end up with
added basic with T plus.
right. Yeah. All right. This is number 25. 25 from chapter 16. It says, so I'm going to draw it out. It's done in empirical formula, but I'm going to draw it out like this. Right? So here you go. And then all they're saying is going to happen is we're going to heat this baby up. Right? A lot of heat, right? So carboxylic acids aren't very reactive, but if you heat something up enough, something's going to happen, right? Whether it decomposes or it does something. So in this case, it actually will do something. So with a lot of heat, right, we already know, are carboxylic acids very good electrophiles? No, they're not. And you notice there's no acid here, right? We're just saying heat, right? Maybe some pressure, I don't know. No acid even. So when you're under a lot of heat, you can imagine, even though we know this isn't that electrophilic, maybe when we heat it up really high temps, it might be. So if this is going to be an electrophile, where's my best nucleophile at? What do you think?
The carbon
We've never seen. Have you ever seen this pi bond act like a nucleophile? No, it's not like an alkene. It's not like a CC pi bond. This pi bond is not like a nucleophile. But what else is in there that has electron density? The OH, right. So what if we just say this OH attacks here, and no, we have to be a neutral mechanism, right? There's nothing else in here. Equilibrium arrows?
Your charges.
Balance thy charges. So we got O minus, We got an OH here. We got an O here that has an H, right? That should be a plus charge on this oxygen, the one that gave up electrons, right? When it lost electrons, when it got them. Okay, well here you go. Now you have a tetrahedral intermediate. Right? So what are we going to do now? You can cry, little tears. Well, the best leaving group right now is what? The thing that just attacked, right? So what do we do if we want to make something else a good leaving group?
Proton transfer.
Proton transfer. Let's transfer a proton. Let's do a PT. All right, we did a proton transfer. So now we turn the water into a pretty good leaving group, right? Or made the water into a leaving group. Tetrahedral intermediate can collapse. And what we've done here is made a what? What have we made? We've made water. And what kind of functional group is this?
It's like an anhydride.
It's
Oh, it is an anhydride.
It is an anhydride. Yeah. But the problem is this, right? Look at all these equilibrium arrows. So we heat the crap out of it. That's great. But what else are we probably going to have to do here to shift equilibrium? What else could we do?
Take out products.
What product would we take out? That's right. Take out the water, right? We'll take out the water. Maybe we could add drying agent. We could put drying agent in our flask. Take out that water, and that would help shift equilibrium this way, right? If we remove one of the products, that will shift equilibrium. So that's probably what they do here. Is they heat it up really high, right above the boiling point of water. They boil the water off, probably. Right? Good. Nice. All right, let's look at number 18 from chapter 16. So, there's one version of this. It said KCN, question mark, H plus, H2O, or H3O plus, question mark. First one should be really easy. Iodine is a good leaving group. KCN is a salt. SN2, backside attack. Draw the right stereochemistry. Get the nitrile. That's the first product, easy. The next step, so we've never used nitriles yet, but they're very similar to carboxylic acids or these carboxylic acid derivatives. So nitriles have a lone pair on the nitrogen, right? And you can imagine this carbon of a nitrile, this carbon right here, is a pretty good electrophile, right? But we want to make it even better, right? So one way we make electrons better is we protonate something they're bonded to. So in this case, we're going to protonate, right, the nitrile. I might run out of room, but we'll see. So that has a plus charge. Remember, water is still floating around. So now this carbon of the nitrile is a pretty good electrophile. So it also helps to know kind of where we're going with this. At the end of the day, we want to turn this nitrile into a carboxylic acid. Right? So we got to start adding oxygens. So we're going to have to add how many molecules of water then? If we're going to turn it into a carboxylic acid, how many oxygens do we need to add? So how many waters do we have to add? 2. Right? So we're adding 1 right now. And if we have a carboxylic acid, we have no N. So somewhere along the line, we're going to get rid of the N. So there we go right there. All right.
I thought in that previous step that the nitrile is breaking off.
Nope, just one bond, right? Just one of its pi bonds broke.
Oh, okay.
Just
That's
one,
the
yep.
C-
Just one pi bond, right? So we still C double bond end here. Yep, still C double bond end. So now we have the water, but we want to keep the oxygen on there. So we need to do what? Good old proton transfer, right? because we want to get rid of this nitrogen. So there's probably going to be a lot of water around, right? It's the solvent. So again, if you look at this, right, this looks like a carbonyl oxygen, right? That's protonated. This is a pretty good electrophile. This carbon right here is pretty delta plus. This nitrogen has a plus charge. So again, right, we knew we had two waters. Water attacks. The nitrogen got the electrons back. Got an OH. Now we got this H2O hanging out. But what do we need to do? At the end of the day, we need to lose nitrogen, right? So what are we going to need to do now? Proton transfer. Absolutely. It's a lot of steps, I know. It's also kind of neat because it also kind of emphasizes how awesome our enzymes in our bodies are. Like they do this kind of stuff like no big deal, right? So now we've made a good leaving group out of this NH3. So we just pick one of these electrons, come down, and kick that out. Equilibrium arrow. Now we're back with an oxygen and OH. There's still an H here. Still a plus charge. We've balanced our charge the whole way. It's been our acidic condition, so we have to have a plus charge. We just lost NH3. So the nice thing about this, NH3 is a gas. These are all equilibrium reactions, arrows, right? So once I get to this point, if I make NH3, it's over. It's bubbling out of the solution, so I'm never going back from this point. So the only thing left to do is regenerate the catalyst, which is when the H plus gives back to the oxygen, the electrons to the oxygen. You end up with a carboxylic acid and then a little H plus left over. And obviously NH3 is gone. But that's how you turn a nitrile into a carboxylic acid.